Section 2 has two very unassuming theorems in them, but they're actually pretty important. And I'll just go on record as saying that these always pop up on the AP exam in one form or another. They're always there. Rolle's theorem is the first one we're going to learn, and the reason we're going to learn Rolle's first is because Rolle's kind of leads to the mean value theorem, which is, in my opinion, a little bit more important, a little bit more useful, but you do need to know Rolle's as well. So Rolle's theorem, Rolle, by the way, is some guy. What? Oh, you figured it out? Oh, okay. If a function is continuous and differentiable, so once again, oh boy. Once again, you have this notation right here, this wording right here. A function is continuous and differentiable. That's almost always going to be the case. Over some interval from a to b. So you have to recognize when you see something that looks like that, what that means. It means that I'm starting somewhere, here's A, and I'm going to B. Okay? This doesn't have to be all positive. The A could be over here, but that's the idea. And f of A is equal to f of B. So now we have a continuous function over the interval from A to B, and f of A is equal to f of B. So that means if the function evaluated at A is here, then the function evaluated at B is in the exact same location. Hopefully you're okay with that. All right. Then, so all of that setup just made this right here. Then there is at least one critical number on the interval. Why is that true?
Because it has to go up or down.
Yeah, the curve that goes in here either looks like this, in which case there's a critical number there, or maybe it looks like this, in which case there's a critical number there, or maybe it looks like this, in which case there's two critical numbers, or maybe it goes crazy, and then it goes like that, and then there's a whole bunch of critical numbers. Okay? That's why it says at least. But there is definitely at least one, because the function is continuous, and that means that the graph has no choice but to change directions somewhere along the way so that it can go back through that other point. Unless it's a horizontal line, and then in which case, why do we care? Because it's just a horizontal line. So in other words, if the value of the function on the endpoints of the interval is the same for both endpoints, then somewhere over the interval there must be at least one critical number, and this is why. Okay? It's just forced into having that be the case. For example, find the x-intercepts of that function and show that f prime of x is equal to 0 somewhere between the intercepts. So we can do that using Rolle's theorem. We can also do it algebraically because this is a very easy function to do. Let's use Rolle's theorem though, first, at least. So find the x-intercepts. How do I find the x-intercepts aside from staring at the graph and pretending that I know if that goes through 1 and 2? When x is 0, you have a y-intercept. That would give me 2. So you set it equal to 0, yeah. This guy right here has to be 0 when y is 0. So now I have x squared minus 3x plus 2 equals 0. Now what? Factor. What do we get? -1 and -2. -1 times -2 is +2. -1 plus -2 is -3. Zero product property and solve x equals 1, x equals 2. Okay, so now we know for sure that those two zeros are at 1 and 2. Why did we care about that? Yeah, so the goal is to show that f prime of x equals 0 somewhere between the intercepts. What is f prime of x equals 0 trying to tell me that I'm trying to find? No. I'm trying to find a critical number. Yeah. So I'm trying to show that there is a critical number somewhere between the intercepts. Somewhere between the x-intercepts. That's the interval, yeah. So my interval here is between 1 and 2. So I could say something like on the interval 1 to 2. The function is continuous. And differentiable. And, so I'm setting up Rolle's theorem here. It does take a little bit of writing. No. And f at 1 equals f at 2 equals 0. What I'm saying there is that the function evaluated at 1 is the same as the function evaluated at 2, and now I'm just telling you what that value is. It's 0. Okay? So that sets up all of the first part of Rolle's theorem. Now, because of all of this, therefore, by Rolle's theorem, there's at least one critical number. Yeah, on the interval. So the problem is asking you to show that f prime of x equals 0 somewhere on the interval. This is showing it right here. Okay? Finding the critical number is as simple as taking the derivative and setting it equal to 0. Okay? But one thing we've started doing and what we're trying to do here and what we're going to move towards as the rest of the course goes on is being able to express the solution in well-written language of calculus. And that's what that is right there. Yeah, it basically is like a proof. But it's really just logic. Don't think of it as like a geometry proof. It's just like a 2-column proof or whatever. We're not going to be doing that. There's other ways you can prove things, and this is one of them. Okay. So if I want to do this just normally, because this is a function that I can differentiate, because that's the thing. I could easily give you a function that you can't take the derivative of. But you can still use Rolle's theorem to prove that there's a critical number somewhere on that interval. Okay? I can give you a function that is differentiable, but that you don't know how to take the derivative of. See what I'm saying? Okay. So now we can find that critical number. If I take the derivative of f of x, I get f prime of x equals 2x minus 3, set it equal to 0, and you get x equals 3/2. And if I look at my graph, it does look like about 3/2 for that critical number. So this is where we're headed when you start doing free response problems. A lot of problems will ask you for some sort of explanation. They'll hide it, show that, or justify, or explain. Those words will clue you into you have to do something like this. And there's going to be a lot of points tied up into those. Each free response problem is worth 9 points. And a lot of times on those free responses, something like this might be 2 or 3 or 4 points of those 9. So you have to know how to do that. Use Rolle's theorem to confirm that there are critical numbers on the interval, closed interval for the function. Then find the critical number. So that means we want to be kind of formal about this. We need to kind of set up Rolle's theorem before we can say that it works. So what do we do? Okay, good. So the first thing we can do is plug in -2 and 2. So we have f of -2 equals -2 to the 4th minus 2 times -2 squared, which is what? 8, okay. And then we'll do the same for the other. F of +2 equals +2 to the 4th minus 2 times 2 to the 4th, which is 8. What? Squared. Sorry, thanks. I was thinking 2 squared is 4. Doing the math in my head as I go. Okay, so what does that tell us? So first of all, this means that f at A equals f at B equals 8. Okay? So I'm just saying right there that that sets up part of Rolle's theorem. The other part of Rolle's theorem is that the function has to be continuous and differentiable. So I don't even have to write the. I could write f of x, or note f of x is continuous and differentiable. So the function is continuous and differentiable, and also f at b is equal to f at a. Does that confirm Rolle's theorem applies? So therefore, Rolle's theorem applies. And there is at least one critical number on the interval. Okay? That's a mathematical way of showing that Rolle's theorem applies. Now that we know that it applies, find the critical numbers. Rolle's theorem will not give us critical numbers. It'll just tell us that there are some. Now we got to find them. So we take the derivative. Then we set it equal to 0. Solve for x, factor 4x out, times, okay, equals 0. Zero product property. So you get x equals 0 here. And now in this one you could factor it into x plus 1 times x minus 1. Or you could just move the 1 over and then take the square root of both sides. Either way you get x equals plus or minus 1. Now the question is, those are all the critical numbers. Are these on our interval? 0 definitely is, and positive and negative 1 are as well. So all three of these then would be our answer. The reason I point that out is because if some of these were not in our interval, then they would not be answers. But all three of these are on the interval, so all three of them are answers. Okay, we're ready for the mean value theorem. If a function f is continuous and differentiable, once again, that same wording, over some interval from a to b. So it starts off looking just like Rolle's theorem. But this time, somewhere on the interval, there's a value c, meaning an x-coordinate c, or an x-value c, such that f prime of c is equal to f of b minus f of a over b minus a. The b and a in that are coming from the endpoints of the interval. Now I have this note here. Both sides of this equation are slope. This is the slope equation right here. M equals y2 minus y1 over x2 minus x1. If you call this 1 and 2, then you have x2 minus x1 here. These are x coordinates for my interval. x2 minus x1, y2 minus y1. This, of course, is a function that gives me the slope anywhere along my function. And if I'm plugging in that x value that I say is giving me this slope over here, then I'm going to wind up with the same thing. So this is a slope, this is a slope. This is the slope at that point C. This is the slope of the secant line. So, in other words, if you find the slope, the secant line is the average rate of change. So if I move this line down to here, I get a secant line. Gives me an average rate of change over that interval. That's actually an incredibly important thing to remember. The secant line is the average rate of change. Between the two endpoints on the interval. Then, by the mean value theorem, somewhere on that interval, the function itself has a slope that is equal to the average rate of change, meaning that the function itself has a slope that is equal to the slope of the secant line. So the instantaneous rate of change would be the slope somewhere, specifically anywhere on that curve. And what this is saying is the instantaneous rate of change at some point over the interval has to be equal to the average rate of change over that interval. And rate of change, of course, can be anything from speed to like a falling object or whatever, okay? So if I take this secant line right here and I just move it down, you can kind of tell that eventually we'll get a tangent line. So on this particular curve, this point right here has the same slope as the slope of the secant line up here. So whatever this number is right here, this x-coordinate, whatever it is, that would be the C that gives you that situation. Okay? So what we're going to do is we're going to calculate the instantaneous rate of change and the average rate of change separately from each other most of the time. It's very easy to calculate this. Then you take the derivative of your function and plug whatever you get for this number into that function, and that will give you the x-coordinate here, which will give you your answer. Okay? When you're done squirming, let me know so that we can move on. You ready? Okay. Mean value theorem is pretty important. Like I said, it pops up on AP, so you kind of need to know it. Let's visualize this one more time. Find the value of C over the interval from 1 to 4 such that f prime at C equals the average slope between the endpoints of the interval for the function. Notice that the function itself is not 100% continuous because of this division by 0 right here. But over the interval from 1 to 4, it is. Okay? So here we are at 1, and here we are at 4. So my function is here, and my function is here. So this would be your A, this would be your B. This will be f at A, this will be f at B. You don't have to do this on your homework problems or whatever. I'm just trying to help you visualize what's going on. So now we take our secant line and put it there. So now what we're going to do is we're going to calculate the slope of the secant line. And we do that using the slope equation, f of b minus f of a over b minus a. So f of b is, we're assuming things by looking at the graph. F of b would be f at 4 equals 5 minus 4 over 4, which is 5 minus 1, which is 4. F at a would be f of 1 equals 5 minus 4 over 1, which is 5 minus 4, which is 1. Can't assume things from the graphs, and make sure you actually do the algebra to come up with those. Okay? So now remember that the mean value theorem is f prime at some value c is going to be equal to f at b minus f of a over b minus a. We can calculate this right now. So f prime of c equals f of b is 4 minus f of a is 1 over 4 minus 1. Okay? So that's 3 over 3, which reduces down to 1. It's kind of a bummer that we wound up with 4 minus 1 over 4 minus 1, because if you got lost here, you might not know where these numbers came from. But this is y2 minus y1 over x2 minus x1. So we get a slope of 1 for the secant line. Now we want to know where the tangent line to the function has the same slope. So I'm going to take that 1 basically and plug it into the derivative, which I haven't calculated yet. So f prime of x is equal to do this derivative, I guess I'll have to rewrite this. 5 minus 4x to the negative first power. We get positive 4x to the negative second power, which is 4 over x squared. Agreed? Okay. So now we got to plug in 1 here. Yeah, we're setting it equal to 1. We're taking our slope of 1 and we're saying, where is my function having a slope of 1? So set it equal to 1, solve for x. 4 equals x squared, square root both sides, x equals plus or minus 2. Well, -2 is not on my interval, but +2 is. So then my answer is x equals 2. And if we look at x equals 2, it does seem like if I move that up there, then it would wind up with a tangent line. So here's the problem. Let's try to draw a picture for this. We're driving to Cody. So let's pretend that this is us and this is Cody, and it's a straight line. If I call this is my first cop and I call this is my second cop, then my position here is 0 and my position here is 5. Just trying to draw a sort of a real simple picture on how to set this thing up. That's right. F at A, my speed at A is 65 miles an hour. F at B, so my speed at B, F at 5 miles down the road, is equal to 60 miles an hour. Okay, now we have to account for the setup for mean value theorem. The setup for mean value theorem is the function has to be continuous and differentiable. Okay, so as I'm driving, am I like warping from spot to spot? No, I can't do that. I have to go in a continuous fashion from point A to point B. Am I suddenly going at different speeds? Like, am I going 65 miles an hour all the way until that second cop sees me and then suddenly I jump down to 60? No. So therefore the function is continuous because I can't warp. It's also differentiable because I can't break my speed and go instantaneously from one speed to another speed, okay? So that graph must be continuous. So for this problem, we can say continuous and differentiable. Those are the requirements for the mean value theorem to work, and we just satisfied them verbally. Okay, so now I want to set up the mean value theorem. The mean value theorem says that the instantaneous velocity equals the average velocity over the interval. So f at b minus f of a over b minus a. So f prime of c, my instantaneous velocity, has to be, at some point on the interval, this. Well, f of b is what? 60 minus f of a, which is 65, over b minus a. Why is this working out this way? Why is it working out like this?
Oh, because we had a higher speed when it was 0 and lower speed.
Doesn't matter. What have I done wrong here? I do. Think about it. What's that? It's not that we need to add in the 3 minutes, it's that this is actually time here. These are time. So this isn't f of 5, it's f of 3. 3 minutes later, I'm going 60 miles an hour. The other issue here is that we're talking now about minutes and miles, or minutes and miles per hour. Okay, so our units here don't match. So I got to turn minutes into hours. How many minutes are there in an hour? So I have 3 minutes, and I want to turn it into hours. 3 over 60 reduces down to 1 over 20. So that's in a 20th of an hour. Okay, now I have units that match. So we have f of b, which is 60 minus 65 over 1/20 minus 0. And we get $100. Yeah, the negative kind of making me mad here, but the reason that it's negative 100 is probably because we've set this up backwards from what it should have been. But that's okay. So we have a speed of negative 100, which we know can't be. So it must be positive 100, because we can't have a negative speed, right? Okay, so 100 is our average rate of change here. At least 100. So these cops saw me going 60 miles an hour and 65 miles an hour, but by the mean value theorem, with my average rate of change of 100 miles per hour, then that means that probably I wasn't driving my truck, first of all. And second, I was going way faster than 100 miles an hour at some point. Okay, so this graph, if I were to graph it, I got 65 miles an hour here, 60 miles an hour here, and I got to have an instantaneous rate of change of 100 miles an hour. My graph must look like this. Somewhere along the way, I have a speed of 100 miles an hour in there. But everywhere else, I'm way above 100 miles an hour. Okay? So these cops actually could prove in a court of law, using this analysis right here, that you were going way, way faster in the span of 3 minutes.
Can they legally do that?
Yes,
Like,
absolutely they could.
They can prove that
Yep,
you're going-
they could. In fact, I've seen, my brother has encountered this also, strips. You know those strips that they put down on the road that usually just count traffic? Well, those strips can be used in this way as well.